Hello again. Welcome to the first part of our fourth lecture video for Thermodynamics course. Today, we will discuss about energy and its transfer. You learned from your science class that energy is the ability to do work. What does it mean? Energy is the ability to cause change in an object. This change can involve either the motion or the position of an object or its particle. Energy is used from the most basic activities to the most complicated ones. People use energy to cook their food, to walk and bicycle, to send astronauts into space, and even to light the modern civilization. Absolutely everything you can think of is using energy in one way or another. Everything in the world is either energy or matter, and even matter, when you really get down to it, it is a kind of energy. What does thermodynamics tell us about energy? In thermodynamics, there is no absolute value of energy, meaning it only deals with change of the total energy. And energy change with some reference. Thus, the total energy of a system can be assigned a value 0 at some reference point. Now let's discuss about energy sources. Energy sources can be categorized as renewable or non-renewable. Renewable energy are sources that can be easily replenished. They are the biomass, hydropower, geothermal, wind, or solar. For the non-renewable energy sources, they are the sources that can be easily replenished. So examples for these are the coal, the natural gas, the oil, and the nuclear energy. These renewable and non-renewable energy sources can be used as primary energy sources to produce useful energy such as heat, or they can be used to produce secondary energy sources such as electricity and hydrogen. Now, we also need to recall what we have learned from the first law of thermodynamics, that energy can be converted from one form to another. For example, the food a person eats contains chemical energy, and a person's body stores this energy until he or she uses it as a kinetic energy during work or play. Another examples are when the stored chemical energy in coal or natural gas and the kinetic energy of water flowing in rivers can be converted to electrical energy, which in turn can be converted to light and heat. Now, look at these animations. These are the different forms of energy. We have the kinetic and potential, we have the elastic energy, we have the chemical, we have the electrical, and lastly, we have the nuclear energy. In thermodynamics analysis, it is often helpful to classify the various forms of energy that make up the total energy of a system into two groups. We have the macroscopic and the microscopic form of energy. In microscopic form, this is the invisible form of energy at atomic and molecular scales. This energy is defined as the energy associated with a random, disordered motion of molecules, and this is due to intermolecular forces. In other words, it is the potential and kinetic energies of individual molecules or atoms. This is popularly known as internal energy U, and it is associated with molecular structure or binding forces and molecular activities, which are the translation, rotation, and vibration motion. In macroscopic form, these are the potential energy and kinetic energy, and these are based on external position and velocity reference respectively. And the difference between the micro and macro potential energy. In macro potential energy, we have the gravitational energy or elastic energy, and for the micro, we have the chemical energy and nuclear energy. Now, take a look at this glass of water. Does a glass of water sitting on a table have any energy? Well, there is no apparent energy of the glass of water on a macroscopic scale. However, in microscopic scale, the kinetic energy is part of internal energy, and the molecular attractive forces are associated with the potential energy. Now let's discuss the kinetic and potential energy. The energy that a system possesses as a result of its motion relative to some reference frame is called kinetic energy. And this is given by 1/2 mv squared, where m is the mass, v is the velocity. Okay? And now, the energy that a system possesses as a result of its elevation in a gravitational field is called the potential energy. And this is expressed as mass times the gravity, acceleration due to gravity, times the elevation. The magnetic, electric, and surface tension effects are significant only in some specialized cases and are usually ignored. In the absence of such effects, the total energy of a system consists of the kinetic, the potential, and internal energies, and this can be expressed as internal energy U plus kinetic energy plus potential energy, and this is equivalent to U plus 1/2 mv squared plus mgz. As you know, the term energy was coined in 1807 by Thomas Young, and its use in thermodynamics proposed in 1852 by Lord Kelvin. The term internal energy and its symbol U first appeared in the works of Rudolf Clausius and William Rankine in the second half of the 19th century, and it eventually replaced the alternative terms inner work, internal work, and intrinsic energy, commonly used at that time. In case of a closed system, the kinetic energy and the potential of energy of a system assumed to be zero, meaning there is no mass flow inside or outside the system, and this system is assumed stationary unless stated. So, in the figure, the mass and energy flow rates associated with the flow of steam in a pipe of inner diameter d with an average velocity VA, this one, V average. Okay, so the mass flow rate is given by m dot is equal to rho times v dot, and this is equivalent to rho times AC times average V. And this is analogous to mass equals rho times velocity, where rho is the fluid density, AC is the cross-sectional area of flow, and the VAVG is the average flow velocity normal to AC. The dot over a symbol is used to indicate time rate throughout this lecture. Okay? For the energy flow rate, this is given by E dot is equal to M dot times E. And this is analogous to E is equal to M small e. Now, let us elaborate what is internal energy. It is the sum of all the microscopic forms of energy of a system, and it is related to the molecular structure and the degree of molecular activity. And this can be viewed as the sum of the kinetic and potential energies of the molecules. To have a better understanding of this internal energy, let us examine a system at the molecular level. The molecules of a gas move through space with some velocity and thus possess some kinetic energy, and this is known as the translational energy. And the atoms of a polyatomic molecules rotate about an axis, and the energy associated with this rotation is the rotational kinetic energy. While the atoms of polyatomic molecule may also vibrate about their common center of mass, and the energy associated with this back and forth motion is the vibrational kinetic energy. For gases, the kinetic energy is mostly due to translational and the rotational motion, with vibrational motion becoming significant at higher temperatures. The electrons in an atom rotate about the nucleus and thus possess rotational kinetic energy. Electrons at outer orbits have larger kinetic energy, and these electrons also spin about their axis, and the energy associated with this motion is the spin energy. Other particles in the nucleus of an atom also possess spin energy. The internal energy is also associated with various binding forces between the molecules of a substance, between the atoms within a molecule, and between the particles within an atom and its nucleus. The forces that bind the molecules to each other are, as one would expect, strongest in solids and weakest in gases. Now, to discuss sensible energy, this is the portion of internal energy of a system associated with kinetic energies of the molecules. Sensible heat is related to changes in temperature of a gas or object with no change in phase, while the latent energy, this is the internal energy associated with the phase of a system, the binding forces between molecules of a substance at constant pressure and temperature. And the other forms of internal energy is the chemical energy, nuclears, and other. The latent heat of fusion is the heat transferred to melt unit mass of solid into liquid or liquid into solid, while the latent heat of vaporization is the quantity of heat required to vaporize unit mass of liquid into vapor or condense unit mass of vapor into liquid. Take a look at this graph. As you see in the graph, if sufficient energy is added to the molecules of a solid or liquid, the molecules overcome these molecular forces and break away, turning the substance into a gas. This is a phase change process. Because of this added energy, a system in the gas phase is at a higher internal energy level than it is in the solid or the liquid phase. The internal energy associated with the phase of a system is called the latent energy. The phase change process can occur without a change in the chemical position of a system. So this is the sensible and latent energy. And for an atom consists of neutrons and positively charged protons bound together by very strong nuclear forces in the nucleus and negatively charged electrons orbiting around it. The internal energy associated with the atomic bonds in a molecule is called chemical energy. During a chemical reaction, such as a combustion process, some chemical bonds are destroyed while others are formed. As a result, the internal energy changes. And for the nuclear forces, which are much larger than the forces that bind the electrons to the nucleus, the tremendous amount of energy associated with the strong bonds within the nucleus of the atom itself is called the nuclear energy. The forms of energy that we already discussed, which constitute the total energy of a system, can be contained or stored in a system, and thus it can be viewed as the static form of energy, while the forms of energy not stored in a system can be viewed as the dynamic forms of energy or as energy interactions. Stored means energy not crossing a boundary of a system. This is given by the change in internal energy of a system is equal to the heat added to the system minus the work done by the system. The dynamic forms of energy or transient form of energy are the energy interactions that crosses boundary of a system, meaning they are recognized as the system boundary as they cross it, and they represent the energy gained or lost by a system during a process. The only two forms of energy interactions associated with a closed system are heat transfer and work. An energy interaction is heat transfer if its driving force is a temperature difference. Otherwise, it is work, as explained in the next section. In mechanics, work is done by a force as it acts upon a body moving in direction of the force. In thermodynamics, work is said to be done by a system if the sole effect on things external to the system can be reduced to raising of a weight. In daily life, we frequently refer to the sensible and latent forms of internal energy as heat, and we talk about heat content of bodies. In thermodynamics, however, we usually refer to those forms of energy as thermal energy to prevent any confusion with the heat transfer. Distinction should be made between the macroscopic kinetic energy of an object as a whole and the microscopic kinetic energies of its molecules that constitute the sensible internal energy of the object as shown in the figure. The macroscopic kinetic energy is an organized form of energy, this one, and is much more useful than the disorganized microscopic kinetic energy of the molecules. Meaning the macroscopic kinetic energy turns the wheel compared to the microscopic state. Okay? So, as you will see in later chapters, the organized energy is much more valuable than the disorganized energy. And a major application area of thermodynamics is the conversion of disorganized energy, this is heat, into organized energy, work. You will see that the organized energy can be converted to disorganized energy completely, but only a fraction of disorganized energy can be converted to organized energy by specially built device called heat engines, like car engines or power plants. A similar argument can be given for the macroscopic potential energy of an object as a whole and the microscopic potential energies of the molecules. Let's end it here and we will continue our lesson about this topic, and I will see you again for the part 2 of this lecture video. Thank you so much for listening.